Hello, and welcome to ZzScience. Wherever you're listening from tonight, I hope you're comfortable. Maybe the lights are low. Maybe you've been thinking about the day. Or maybe you're just ready to let it all go for a while. Either way, we'll take our time with this. Tonight we're going somewhere quiet, somewhere vast. We're going to talk about the hidden structures of the universe, the scaffolding that holds everything together, the patterns we didn't even know were there until recently. Galaxy clusters, filaments that stretch across impossible distances. Voids so empty they make the word nothing feel inadequate. But we won't rush it. There's something calming about thinking on this scale. It puts things in perspective, yes, but it also just slows you down, makes you breathe a little deeper. So let's ease into it. When you look up at the night sky, you see stars. Thousands of them, if you're lucky enough to be away from city lights. And for most of human history, that was the universe. Stars scattered across a dome of darkness, some brighter, some dimmer. Patterns we turned into stories. But even then, people noticed something. The stars weren't completely random. They were clusters. Dense patches where more stars seemed to gather. The Pleiades, for instance, that little group that looks almost like a tiny dipper. You can see it with your naked eye, and humans have been looking at it for tens of thousands of years. We like patterns. We look for them instinctively. And as we built better tools, telescopes, cameras, computers that could map the positions of millions of objects, we started seeing patterns on scales we never imagined. Not just clusters of stars within our own galaxy, but clusters of galaxies themselves. Whole galaxies, hundreds of them, bound together by gravity into structures so large they take millions of light years to cross. And then, we noticed those clusters weren't scattered randomly either. They were connected. Let's step back for a moment. Let's talk about what a galaxy cluster actually is. Our galaxy, the Milky Way, is home to a few 100 billion stars. It's enormous by any measure we can really comprehend. But the Milky Way doesn't float alone in space. It's part of something called the local group. A collection of about 50 galaxies, all gravitationally bound to each other. Most of them are small, dwarf galaxies, but there are a few big ones. Andromeda, our nearest large neighbor, is part of the local group. So is Triangulum. The local group itself spans about 10 million light-years across, and yet, on the cosmic scale, it's barely a footnote. Because the local group is just a small part of something much, much larger. It's part of the Virgo supercluster. The Virgo supercluster contains thousands of galaxies, organized into smaller groups and clusters, all loosely held together by gravity. At its heart is the Virgo cluster itself, a dense concentration of over 1,000 galaxies, sitting about 54 million light-years away from us. That cluster is so massive, so gravitationally dominant, that it's actually pulling the local group toward it. Slowly, very slowly, but inexorably. We're falling toward Virgo, and we have been for billions of years. This kind of structure, superclusters containing clusters containing groups containing galaxies, this was one of the first hints that the universe had organization beyond what we expected. It wasn't just stars and galaxies scattered like grains of sand. There was hierarchy. There was architecture. But even that wasn't the whole picture. In the 1980s, astronomers started creating maps. Not maps of individual galaxies, but maps of where galaxies were in space. Three-dimensional maps showing the distribution of hundreds, then thousands, then millions of galaxies across the observable universe. And when they looked at those maps, they saw something astonishing. The galaxies weren't evenly distributed, not even close. Instead, they formed a pattern that looked almost biological, like a sponge, like a web. Long filaments of galaxies stretching across hundreds of millions of light years, connecting dense nodes, the clusters, with each other. And between the filaments, vast empty regions, voids, places where almost no galaxies existed at all. They called it the cosmic web. It's one of the most beautiful structures in all of nature, and most people have never seen an image of it, because it's too big, too abstract. You can't take a photograph of the cosmic web the way you can photograph a galaxy or a nebula. You have to plot it, map it, infer it from the positions of millions of distant lights. But once you see it, you can't unsee it. The universe has a skeleton, a framework, and we're embedded in it, moving through it, part of it, without ever really noticing in our day-to-day lives. So how did this structure form? That's a question that takes us back to the beginning, almost to the very beginning. In the first few 100,000 years after the Big Bang, the universe was hot and dense and nearly uniform. Matter was spread out almost evenly, but not quite. There were tiny fluctuations, regions that were just slightly denser than others. We're talking about differences of 1 part in 100,000, almost nothing. But in a universe governed by gravity, almost nothing is enough. Those slightly denser regions had a little more mass, and a little more mass meant a little more gravitational pull. So they started attracting nearby matter. Slowly at first, but as they grew, they attracted more and more, and the process fed itself. Meanwhile, the less dense regions, the places where matter was slightly more spread out, those places lost matter to the denser regions. They became emptier and emptier. Over hundreds of millions of years, this process carved the universe into the structure we see today. Dense filaments and clusters formed where matter had been just slightly more concentrated. Voids formed where it had been just slightly more sparse. It's a pattern that emerges naturally from gravity and time. You see similar patterns in other systems. Foam on the surface of water, the structure of lung tissue, mycelium spreading through soil. Nature likes these kinds of networks. They're efficient. They maximize connectivity while minimizing the material needed to create the connections. But the cosmic web it's hard to describe the scale. One of the largest structures we've ever identified is called the Hercules Corona Borealis Great Wall. It's a filament, a concentration of galaxy clusters that stretches for about 10 billion light years. 10 billion. That's more than 2/3 the radius of the observable universe. When light left one end of that structure, the Earth didn't even exist yet. Wouldn't exist for billions of years. And it's not unique. We've found other structures almost as large. The Sloan Great Wall, the huge large quasar group. These names don't quite capture the strangeness of what they represent. We're not good at naming things on this scale. Let's zoom in a bit. Let's talk about what these filaments actually are. Imagine a thread stretching across space. But this thread is made of galaxies, thousands of them, arranged in a rough line, sometimes braided, sometimes splitting into smaller strands, sometimes converging into thick knots. The thread isn't solid. Galaxies are separated by millions of light years, even within the filament. But there's a clear concentration, a clear direction. These filaments aren't static either. They're dynamic. Galaxies are moving within them, flowing along the gravitational channels like water in a riverbed. Some galaxies are falling into the clusters at the nodes, where the filaments intersect. Others are being pulled along the length of the filament, accelerating as they go. It's all very slow by human standards. A galaxy might take 1 billion years to travel the length of a filament. But it's happening. The cosmic web is alive with motion, even if we can't see it directly. And here's something that took astronomers a long time to realize. Most of the mass in these filaments isn't in the galaxies themselves. It's in the dark matter. Dark matter is one of those terms that sounds more mysterious than it needs to. It's not made of darkness. It's not evil or strange in some metaphysical sense. It's just matter that doesn't interact with light. It doesn't emit light, doesn't reflect it, doesn't absorb it. It's invisible to all of our telescopes, no matter what wavelength they observe in. But it has mass. And mass means gravity. And gravity is something we can measure. We know dark matter exists because we can see its effects. Galaxies rotate faster than they should based on the visible matter alone. Galaxy clusters hold together more strongly than the visible galaxies can account for. Light from distant objects bends as it passes through seemingly empty space, bent by the gravity of something we can't see. Dark matter is everywhere. In fact, it makes up about 85% of all the matter in the universe. The stuff we're made of, atoms, protons, neutrons, electrons, all the matter that makes up stars and planets and people, that's just 15%, a minority. And in the cosmic web, dark matter is the scaffold. The structure formed first in dark matter, because dark matter doesn't interact with light or normal matter in the early universe the way normal matter interacted with itself. Dark matter could clump freely, forming the gravitational wells that eventually attracted normal matter, the gas that would become galaxies. So when we talk about filaments connecting galaxy clusters, we're really talking about dark matter filaments. The galaxies are just tracers. They're the visible component of a much larger, invisible structure. It's a little humbling, isn't it? The universe we see is just the tip of the iceberg. Most of what's out there is hidden from us. We navigate by its gravity, not by its light. There's something almost poetic about the cosmic web when you think about it. All these galaxies, scattered across billions of light years, and yet they're connected. Not in any way we can experience directly. There's no traveling between galaxies in the web, no communication, no interaction beyond gravity. But the connection is real. We're part of a network. The Milky Way sits within a filament. That filament connects us, tenuously, to other clusters, other superclusters, stretching away in all directions. We're not isolated. We're embedded in something larger. And yet, at the same time, there are vast regions where that connection breaks down entirely. The voids. Let's talk about emptiness for a moment. Real emptiness. Not the emptiness of interstellar space, which is mostly empty, but still contains a few atoms per cubic centimeter. Still has the occasional dust grain. Still has starlight passing through. Not the emptiness between galaxies within a cluster, which is mostly empty but still has hot gas, still has the occasional stray star, still has dark matter. No, the voids are different. A cosmic void is a region of space where almost no galaxies exist. They're enormous, typically 100 to 300 million light-years across. Some are larger. Inside a void, the density of galaxies might be 10% of the average density of the universe, or less. Imagine flying through a void. You'd leave the filament, leave the last faint galaxies behind, and then nothing. For millions of light years in every direction, nothing. No galaxies, No stars visible except as unimaginably faint points of light at the very edge of perception. The cosmic microwave background, that faint glow left over from the Big Bang, would be the brightest thing in the sky. It would be the loneliest place in the universe. But here's the thing about voids. They're not completely empty. There's still dark matter in them, just much less than in the filaments. There's still the occasional dwarf galaxy, small and faint and isolated. There's still space itself, expanding, carrying the distant filaments farther and farther away. Voids are what you get when you take away almost everything. But almost is doing a lot of work in that sentence. We didn't know voids existed until the 1970s. That's surprisingly recent. Astronomers were mapping the positions of galaxies, trying to understand how they were distributed, and they kept finding these gaps, regions where their surveys just came up empty. At first, they thought maybe it was a problem with their instruments, or with the way they were selecting which galaxies to observe. But the gaps were real. And they were huge. One of the first voids discovered was called the Beauties Void. It's about 300 million light-years across. When it was first mapped, astronomers found only 60 galaxies in the entire volume, a region where you'd expect to find thousands. It was almost eerie, like finding a hole in the fabric of the universe. But as we mapped more of the sky, we realized voids weren't unusual. They were common. In fact, they make up most of the volume of the universe. The filaments and clusters, the places where galaxies congregate, those are the dense regions, but they're also the rare regions in terms of volume. Most of space is void. We live in a filament, so our perspective is skewed. We're surrounded by galaxies. The night sky is full of them if you have a big enough telescope. But most places in the universe aren't like where we are. Most places are empty. There's a question that comes up sometimes when people learn about voids. It's a natural question. If you were in the middle of a void, would you know? Would it feel different? And the answer is probably not. Not immediately. If you were standing on a planet orbiting a star in a small dwarf galaxy in the middle of a void, your sky would look different. There'd be fewer galaxies visible, and the ones you could see would be more distant, fainter. But your daily life, assuming you have a daily life, which is a big assumption, would be the same. Your sun would rise and set. Your planet would orbit. The laws of physics would be unchanged. You'd just be more alone, more isolated. And maybe you wouldn't even know it. Maybe your civilization would develop, would build telescopes, would map the universe, and only then would you realize we're in the middle of nowhere. The nearest galaxy cluster is 100 million light-years away. We're surrounded by emptiness. Would that change how you thought about your place in the universe? Maybe. Maybe not. Isolation is strange like that. It's only meaningful if you know what you're isolated from. The cosmic web isn't static. It's still forming, still evolving. Galaxies are still flowing along the filaments, still falling into clusters. Clusters are still merging with each other, creating larger structures. Voids are still expanding, pushing the filaments farther apart. And, underlying all of this, driving it all, is dark energy. Dark energy is even stranger than dark matter. If dark matter is invisible mass that we detect through gravity, dark energy is invisible energy that we detect through the accelerating expansion of the universe. It makes up about 70% of the total energy content of the universe, and it's pushing space itself apart. In the early universe, Gravity was winning. Matter was clumping together, forming the cosmic web, fighting against the expansion. But about 5 or 6 billion years ago, something changed. The universe had expanded enough that matter was more spread out, and the gravitational attraction between distant structures weakened. Dark energy, which had always been there but had been overwhelmed by gravity, started to dominate. And the expansion started accelerating. This has profound implications for the future of the cosmic web. Right now, structures that are gravitationally bound, galaxy clusters for instance, will stay together. The dark energy can't overcome the gravity holding them together. But structures that aren't bound, the filaments connecting distant clusters, the voids between them, those are being stretched. The distances are growing. Eventually, billions of years from now, the cosmic web will start to break apart. The filaments will thin out as the galaxies in them drift farther apart. Voids will grow larger. Clusters will become more isolated. In the very distant future, trillions of years from now, each cluster will be alone, surrounded by darkness. The light from other clusters will have been redshifted into invisibility by the expansion of space. If there are any civilizations left then, they'll look up at the sky and see only their own galaxies. No evidence of anything beyond. They'll have no way to know about the cosmic web, no way to know they're part of something larger. Because by then, they won't be. They'll be truly isolated. It's a melancholy thought in a way, but it's also very far in the future. For now, we can still see the structure. We can still map the connections. Let's come back to the present. Let's talk about what it means to actually map the cosmic web. When astronomers create these maps, they're not taking pictures. Not exactly. What they're doing is measuring redshift. Light waves stretch as they travel through expanding space. The farther the light has traveled, the more it stretches, and stretched light is redder, shifted toward the red end of the spectrum. By measuring how much a galaxy's light has been redshifted, astronomers can determine how far away it is. Then, they do this for millions of galaxies. They measure the position on the sky and the redshift, the distance for each one. And, slowly, painstakingly, they build up a three-dimensional map. Some of the largest surveys have mapped tens of millions of galaxies. The Sloan Digital Sky Survey. The 2DF Galaxy Redshift Survey. More recently, projects like the Dark Energy Spectroscopic Instrument, which is mapping tens of millions of galaxies across more than a third of the sky. And when you plot all those points, millions of them, each one representing an entire galaxy, the cosmic web emerges. You see the filaments, you see the clusters, you see the voids. It's one of the most beautiful datasets in all of science. A map of everything. But here's something that's easy to forget when you're looking at those maps. Each point is a galaxy, and each galaxy contains hundreds of billions of stars. And many of those stars have planets. And on some of those planets, maybe, possibly, there's life. The cosmic web isn't just a physical structure, it's a map of possibilities. Every node in the network is a place where complexity can exist. Where stars are born, where planets form, where, maybe, consciousness arises and looks out at the universe and wonders what it all means. We're not separate from the cosmic web. We're in it. We're made of matter that was once part of the primordial soup, that clumped into the filaments, that fell into the gravitational well that became the Milky Way, that condensed into the sun and the planets, that formed the earth, that became life, that became us. The atoms in your body have been on a journey that spans the age of the universe. They've been part of the cosmic web from the very beginning. Let's slow down for a moment. Let's just think about scale. A light year is the distance light travels in a year, about 6 trillion miles. It's already an incomprehensible distance. The nearest star to the Sun is about 4 light years away. The Milky Way is about 100,000 light years across. That's 25,000 times farther than the nearest star. The distance to the Andromeda Galaxy, our nearest large neighbor, is about 2.5 million light years, 25 times the width of the Milky Way. The distance to the Virgo cluster, the heart of our supercluster, is about 54 million light years, about 20 times farther than Andromeda. And the cosmic web? The filaments stretching across the universe? Some of them are billions of light years long. These distances are so large that even light, traveling at the ultimate speed limit of the universe, takes eons to cross them. When we look at a distant galaxy cluster, we're not seeing it as it is now. We're seeing it as it was billions of years ago, when the light left it. Some of those galaxies might not even exist anymore. They might have merged with others, or been torn apart, and we won't know for billions more years. The cosmic web is as much a map in time as it is in space. Every point on the map represents a different moment in the history of the universe. There's something meditative about thinking on this scale. It puts everything in perspective, and I mean everything. Your worries, your plans, your entire life. Not in a nihilistic way, not in a way that makes things meaningless, but in a way that's almost relaxing. You're part of something so vast, so ancient, so intricate. You didn't ask to be. You just are. And that's okay. The cosmic web doesn't care about you, but it's not indifferent either. It's not conscious. It's just structure. Patterns emerging from simple rules and unfathomable amounts of time. And somehow, somewhere in that structure, matter organized itself in just the right way to become you. To become aware. To look back at the web and recognize it. That's not nothing. Let's talk a bit more about the clusters themselves, the nodes where the filaments meet. Galaxy clusters are some of the most extreme environments in the universe. You have hundreds or thousands of galaxies, each containing billions of stars, all packed into a relatively small volume of space. They're orbiting each other at incredible speeds, hundreds or even thousands of kilometers per second. And they're constantly interacting. When galaxies pass close to each other in a cluster, tidal forces can strip away their outer regions. Stars can be pulled out into long streams or scattered into the space between galaxies, forming what's called the intra-cluster medium. Gas can be stripped away even more efficiently because it's less tightly bound than stars. And sometimes, galaxies collide. People often imagine galaxy collisions as violent, catastrophic events. Explosions of stars smashing into each other. But that's not quite right. Galaxies are mostly empty space. When two galaxies collide, their stars very rarely actually hit each other. The distances between stars are just too large. What does collide is the gas. The clouds of hydrogen and helium that fill the space between stars. When those collide, they heat up, they compress, and sometimes that compression triggers a burst of star formation. New stars forming from the shocked gas, lighting up in bright clusters. Over time, millions of years, the two galaxies will orbit each other, slowly losing energy to friction and gravitational interactions. And eventually, they'll merge. They'll become one galaxy, larger than either of the originals. This happens all the time in galaxy clusters. The largest galaxies in the universe, the so-called brightest cluster galaxies, are thought to have formed through repeated mergers. They sit at the centers of galaxy clusters, bloated and elliptical, having cannibalized dozens or hundreds of smaller galaxies over billions of years. It's a slow kind of violence, cosmic in scale and timescale, but violence nonetheless. And yet, in between all of this activity, there's also stillness. The intracluster medium, the space between galaxies in a cluster, isn't empty. It's filled with hot gas, extremely hot, tens of millions of degrees, so hot that it glows in X-rays. This gas was heated by the gravitational energy of the cluster itself. As matter fell into the cluster, it accelerated, converting gravitational potential energy into kinetic energy. And when that matter collided with other matter, the kinetic energy became heat. The intracluster medium is one of the hottest places in the universe, and yet it's also incredibly thin. There might be only a few atoms per cubic centimeter, thinner than the best vacuum we can create in laboratories on Earth. So it's both intensely hot and almost perfectly empty. It's a strange duality. If you could float in the intracluster medium, which you can't because you'd be instantly vaporized by the heat, but let's imagine, you'd be surrounded by galaxies. Hundreds of them, scattered in all directions, some closer, some farther. And between you and them, almost nothing. Just the faint glow of X-ray light from the gas, invisible to other human eyes, but detectable by our instruments. It would be beautiful in a stark, alien way. The cosmic web is often described as the largest structure in the universe, and that's true in a sense. But it's worth being clear about what that means. The cosmic web isn't a single object. It's a pattern, a distribution. It's the collective arrangement of all the matter in the universe. So when we say it's the largest structure, we're really saying this is the scale at which structure stops. Beyond this, the universe looks roughly the same everywhere, homogeneous, isotropic. This is important because it relates to one of the fundamental assumptions of modern cosmology, the cosmological principle. The idea that, on large enough scales, the universe is the same everywhere. No matter where you are, if you zoom out far enough, you'll see the same average density, the same cosmic web pattern, the same ratio of filaments to voids. This principle is what allows us to apply the laws of physics everywhere in the universe. It's what makes cosmology possible as a science. But it's also humbling, because it means we're not in a special place. The cosmic web looks the same from here as it would from a galaxy in a distant supercluster. We're just one filament among countless others, one cluster among millions. Copernicus told us we're not at the center of the solar system. Hubble told us we're not at the center of the galaxy or the universe. And the cosmic web tells us we're not even in a particularly special part of the structure. We're just somewhere, embedded in the pattern like everywhere else. Let me tell you about one specific structure, one filament, just to make this feel a bit more concrete. There's a filament called the Pisces-Cetus supercluster complex. It's about 1 billion light-years long and 150 million light-years wide. It contains dozens of galaxy clusters and thousands of individual galaxies. It's one of the largest structures we've identified. And the thing is, even a structure that large isn't unique. We've found others like it. The Sloan Great Wall, the CFA2 Great Wall, the Sculptor Wall. When we say these things are walls, we don't mean solid barriers. We mean regions where galaxies are more concentrated, sheet-like structures sometimes, where filaments have spread out and merged, or linear structures where a single filament dominates. The names are poetic but also inadequate. How do you name something 1 billion light-years long? How do you even conceptualize it? Astronomers use the names of constellations usually. The parts of the sky where the structure appears to us. But that's arbitrary. The constellations are from our perspective. From another galaxy, the same structure would appear in a completely different part of the sky. We're trying to map something universal, using names and reference frames that are deeply local. It's the best we can do. Here's a thought experiment. Imagine you're an astronomer on a planet, orbiting a star in a galaxy in the Pisces-Cetus supercluster complex. You're looking out at the universe, mapping galaxies, just like we are. From your perspective, your filament, the Pisces-Cetus complex, would be the most prominent feature in your maps. You'd see it stretching across the sky, packed with galaxies, defining your cosmic neighborhood. And you'd see other filaments, more distant, stretching away in other directions. You might see our filament, the one that contains the Milky Way and the Virgo supercluster. It would be far away, but you'd be able to map it. You'd give it a name based on the constellations in your sky, something that would mean nothing to us. And if you were really ambitious, if you mapped enough of the universe, you'd eventually realize that your filament and ours are part of the same structure, that they're connected, somewhere, by other filaments, that we're all part of one vast web. You'd never be able to communicate with us. The distances are too large, the timescales too long, but you'd know we're out here, somewhere, embedded in the same cosmic structure. There's something comforting about that, isn't there? The idea that even across incomprehensible distances, there's a connection. Not a personal connection, not a meaningful one in any human sense, but a structural one, a shared context. I want to pause here and acknowledge something. We've been talking about the cosmic web for a while now, and it's easy for this to become abstract, just shapes and numbers and scales that don't connect to anything real. But the cosmic web is real. It's made of matter, real atoms, real galaxies, real light. It exists out there, right now, whether we think about it or not. And we're part of it. Not metaphorically, actually part of it. Every breath you take involves atoms that were once part of the cosmic web. The calcium in your bones was forged in a star that was part of a galaxy that was part of a filament. The water you drink contains hydrogen that has existed since the first few minutes after the Big Bang, that has been part of the cosmic web since structure first began to form. You are, quite literally, made of the same stuff as the filaments and the clusters and the voids. You're not separate from the universe. You're a local, temporary arrangement of universe stuff. And that stuff has been on a journey. From the Big Bang to the formation of the first structures, to the collapse of gas clouds into stars, to the supernova explosions that scattered heavy elements into space, to the formation of the solar system, to the Earth, to life, to you. The cosmic web isn't just out there, it's also in here, in you. Let's talk about time for a moment, specifically the deep time embedded in the cosmic web. The structure we see today took billions of years to form. When we look at a galaxy cluster, we're seeing the end point, for now, of a process that started when the universe was young. The tiny density fluctuations in the early universe, amplified by gravity, growing slowly into the filaments and clusters we see today. But that process isn't finished. It's still ongoing. Galaxies are still flowing along filaments. Clusters are still accreting matter. Voids are still expanding. In 1 billion years, the cosmic web will look different. Not drastically different, but different. Some clusters will have grown larger. Some filaments will have thinned out. Some small structures will have merged into larger ones. And if you could speed up time, watch the evolution of the cosmic web in fast forward, you'd see it almost like a living thing. Growing, shifting, evolving. Filaments reaching out and connecting. Clusters forming at the nodes. Voids inflating like bubbles. It would be beautiful. And it would be completely impersonal. The cosmic web doesn't have intentions. It doesn't grow toward anything. It's just matter responding to gravity, playing out over billions of years. But, from our perspective, embedded in the structure, living on timescales of decades rather than eons, it seems frozen, unchanging. We can measure its evolution only by looking at distant structures, seeing how the web was different billions of years ago when the light we're now receiving first left them. We're like mayflies looking at a forest. We can see the forest, but we can't see it grow, not in our lifetimes. We can only infer its growth by looking at trees of different ages, by studying rings in old trunks, by building models of how forests develop over centuries. There's a specific technique astronomers use to study the cosmic web that I think is worth mentioning. It's called gravitational lensing. Remember how dark matter doesn't emit or absorb light, but it does have gravity? Well, gravity bends light. Einstein showed this. When light from a distant galaxy passes through a region with a lot of mass, like a galaxy cluster or a section of a filament, it bends. And from our perspective, that makes the background galaxy appear distorted, stretched sometimes into arcs or even complete rings. By studying these distortions, astronomers can map the distribution of mass in the foreground structure. Not just the visible matter, the galaxies, but all of the matter, including the dark matter. And what they found is that the dark matter distribution matches the cosmic web pattern. It's concentrated in the filaments and clusters, just like the galaxies. But the dark matter is more smoothly distributed, less clumpy. It forms the underlying structure, and the galaxies trace out the densest parts of that structure. So when we map the cosmic web using galaxies, we're really mapping the peaks of the dark matter distribution. The galaxies are snowflakes on the surface of a dark mountain range. And the lensing studies confirm this. They show that the filaments aren't just lines of galaxies. They're three-dimensional tubes of dark matter with galaxies embedded in them like jewels in a setting. It's dark matter that defines the structure. Normal matter just goes along for the ride. All right, let's take a breath. We've covered a lot of ground. The formation of structure in the early universe, the cosmic web and its filaments, clusters and voids, the role of dark matter as the underlying scaffold, the scales involved, the incomprehensible distances, the deep time. In part 2, we'll slow down even more. We'll drift into the voids. We'll talk about what it means for something to be empty. We'll explore the architecture of dark matter in more detail. And we'll think about the quiet spaces between the lights. But for now, just let these ideas settle. The cosmic web, the hidden structures of the universe, the pattern that connects everything, including you. The cosmic web is a lot to take in. All those filaments stretching across the universe, all that dark matter holding everything together, all those galaxies flowing along invisible highways of gravity. It's beautiful, yes, but it's also strange and vast, and maybe a little unsettling if you think about it too hard. In this part, we're going to explore the quieter side of the cosmic web, the empty spaces, the voids, the regions where galaxies don't go. And we're going to think more carefully about dark matter, not just as scaffolding, but as something that defines the very shape of space itself. Let's ease into it. When we think about space, we usually think about the things in it. Stars, planets, galaxies, the stuff that emits light, that we can see and photograph and study. But most of space isn't like that. Most of space is, well, space. empty, or nearly empty. Even between stars within a galaxy, the density of matter is incredibly low, a few atoms per cubic centimeter on average. In interstellar space, you could travel for light years and never encounter more than a few hydrogen atoms per liter of volume. But that's nothing compared to the voids. In a cosmic void, the density drops even lower, much lower. You might have one galaxy where you'd normally expect 10. And between those rare galaxies, the density of normal matter approaches zero. Not quite zero. Nothing in the universe is truly zero, but close enough that the distinction hardly matters. So what does that mean? What is a void, really? A void is a region of space where the gravitational potential is unusually flat, where there's not enough mass to create strong gravitational wells, where, if you were a particle of dark matter or a stray atom of hydrogen, you drift slowly, unperturbed, for millions or billions of years. Voids aren't pulling things together the way filaments and clusters are. They're not collapsing under their own gravity. They're just there, gently expanding with the rest of the universe, but not doing much else. And yet, they're not completely empty. There's still the fabric of space-time itself, which is something. There's still the pervasive hum of the cosmic microwave background, which fills all of space. There are still neutrinos streaming through, and photons from distant galaxies, and the occasional cosmic ray. There's still dark energy, which is the same everywhere, in voids, in filaments, in clusters. Dark energy doesn't care about structure. It just pushes space apart, wherever space exists. So voids aren't nothing. They're just the universe in its simplest, most undisturbed state. Space with very little matter in it. Space being allowed to do what it naturally does, which is expand. Here's a question that bothered cosmologists for a while. If voids are regions where matter is sparse, why do they exist at all? Why didn't gravity pull all the matter out of those regions and into the filaments and clusters? The answer has to do with timing, with the history of structure formation. In the very early universe, matter was distributed almost evenly. Almost, but not quite. There were tiny fluctuations, regions that were slightly denser or slightly less dense than average. The denser regions collapsed first. Gravity amplified the density contrasts. The dense got denser, and as they pulled matter in, they pulled it away from the less dense regions. But here's the key. The less dense regions didn't have much matter to begin with. So even though some of it got pulled away into the forming filaments, there wasn't enough gravitational attraction to pull all of it away. The voids didn't collapse because there wasn't enough mass in them to make them collapse. Instead, they expanded. As the universe expanded, the matter in the voids got more spread out. And as the filaments and clusters grew denser, the contrast between them and the voids grew sharper. So voids are, in a sense, the original state of the universe, slightly under-dense regions, preserved and amplified by the expansion of space. They're fossils of the early universe, stretched and diluted by billions of years of cosmic growth. Imagine being in a void. Really try to picture it. You're floating in space. Maybe you're on a planet, but let's keep it simple. Just you, floating, somehow surviving in the vacuum, looking around. In every direction, you see almost nothing. No Milky Way arcing across the sky. No nearby galaxies glowing softly in the darkness. No dense star fields. Just a few faint smudges of light scattered here and there, so distant they're barely visible. Those are galaxies, but they're hundreds of millions of light years away, far beyond the edge of the void. The brightest thing in the sky is the cosmic microwave background. But you can't see that with your eyes. It's too faint, too redshifted into the microwave part of the spectrum. If you could see it, it would be a faint, uniform glow coming from every direction at once. The afterglow of the Big Bang, cooled and stretched by the expansion of the universe. It would be profoundly lonely. Not in an emotional sense. You're just imagining. There's no one there to feel lonely. But in an existential sense. You're in a place where almost nothing has ever happened. Where almost nothing ever will happen. There are no stars forming in a void, no supernovae, no black holes, no bustling galaxies. Just empty space, slowly expanding, carrying the distant filaments farther and farther away. But let's not get too poetic about it. Let's think about what's actually there in physical terms. Even in a void, there's dark matter. Not much, but some. The dark matter forms a kind of tenuous web within the void, a faint echo of the larger cosmic web. If you could see dark matter, a void wouldn't look completely empty. It would look like a faint mist, very thin, with perhaps a few slightly denser wisps here and there. Those wisps are where the rare galaxies in the void have formed. Small dwarf galaxies usually. Places where the dark matter was just slightly denser than average, enough to pull in some normal matter and start forming stars. But these void galaxies are strange. They're isolated. They haven't interacted much with other galaxies. They haven't been stripped of their gas by passing through a cluster. They haven't merged with neighbors. They're pristine in a way, undisturbed. Astronomers find void galaxies interesting for this reason. They're natural laboratories for studying galaxy evolution without all the complications of interactions and mergers. They're galaxies that have been left alone, evolving quietly in the emptiness. There's a particular void that astronomers like to talk about. It's called the Boötes void, and I mentioned it earlier. It's about 300 million light-years across, and it contains only about 60 galaxies. That's astonishingly empty. For comparison, a typical region of that size outside a void would contain about 2,000 galaxies. When the Boötes void was first discovered in the 1980s, it was so empty that some astronomers joked it might be artificial. The work of some incredibly advanced civilization that had cleared out the space for who knows what. A construction project on the grandest scale imaginable. Obviously, that's not what it is. It's just a void. A natural consequence of structure formation. But the joke reveals something about our instincts. We see patterns, and we want to explain them. We see emptiness, and we want to fill it with meaning. Even when the answer is simpler. Sometimes, space is just empty. Let's think about dark matter again, but more carefully this time. We know dark matter exists because of its gravitational effects. We can measure those effects in several ways. The rotation curves of galaxies, the way stars orbit around galactic centers, indicate there's more mass present than we can see. The motion of galaxies within clusters and the temperature of the hot gas in clusters both indicate the same thing. And then there's gravitational lensing, which I mentioned before. The bending of light by massive objects. When we observe lensing around galaxy clusters, we can map the distribution of mass. And what we find is that most of the mass isn't in the visible galaxies. It's in a diffuse halo surrounding them. Dark matter. But here's the thing. We don't know what dark matter is made of. We have theories, lots of them. Weakly interacting massive particles, or WIMPs, axions, sterile neutrinos, primordial black holes. Each has its proponents and its problems. We've built detectors deep underground, shielded from cosmic rays, trying to catch dark matter particles as they pass through the Earth. So far, we haven't detected anything definitively. Dark matter, if it's made of particles, interacts so weakly with normal matter that it passes right through us without a trace. Billions of dark matter particles might be passing through your body right now, every second, and you'd never know. It's invisible, intangible, and yet it makes up most of the matter in the universe. It's the reason galaxies don't fly apart. It's the reason the cosmic web has the shape it does. It's strange to think about. This substance that we've never directly detected, that we know almost nothing about, is the most important component of the large-scale structure of the universe. Here's a thought experiment that might help make dark matter feel a bit more real. Imagine the universe without dark matter. Just take it away. Leave only the normal matter, the atoms, the stars, the gas. What would happen? Well, first, galaxies would change. Without dark matter halos to hold them together, the outer regions of galaxies would fly apart. The stars there are moving too fast to be held by the gravity of the visible matter alone. They'd escape, drifting off into intergalactic space. Galaxy clusters would also fall apart. The galaxies in them are moving at hundreds or thousands of kilometers per second. Without the extra gravity from dark matter, they'd overcome the gravitational pull of the cluster and disperse. And the cosmic web? It wouldn't exist. Or it would exist in a much weaker form. The filaments would be less defined. The clusters would be smaller and less massive. The voids would be less empty because there wouldn't be as much gravitational attraction pulling matter into the dense regions. In short, the universe would be a much less structured place. Simpler, maybe, but also less interesting. Less capable of forming the complex structures, like galaxies, stars, planets, life, that make the universe worth thinking about. Dark matter is essential, not because it does anything directly to us, but because it creates the conditions in which everything else can happen. Let's return to the filaments for a moment. I want to talk about them in a bit more detail. When we say filaments connect galaxy clusters, we don't mean they're like roads or pipelines. There's no hard boundary, no clear edge where the filament ends and the void begins. It's more like a gradient region where the density of galaxies is higher, fading smoothly into regions where it's lower. And within a filament, galaxies are moving. They're not stationary. They're falling along the gravitational gradient toward the clusters at the ends of the filament. This motion is slow by human standards. It might take hundreds of millions of years for a galaxy to travel the length of a filament. But it's significant on cosmic timescales. It's how clusters grow. Galaxies fall into them along the filaments, adding to the cluster's mass, contributing to its evolution. And as galaxies move through the filaments, they're affected by the environment. The intergalactic medium, the thin gas that fills the space between galaxies, can strip away some of a galaxy's gas. This is called ram pressure stripping. It's like driving a car through a strong wind. The wind pushes against you, and if you're not careful, it can tear things off. For a galaxy moving through a filament, intergalactic medium is the wind. And the galaxy's gas is what gets stripped away. This can shut down star formation because stars form from gas. Without gas, no new stars. So filaments aren't just passive structures. They're active environments that shape the galaxies within them. There's a specific prediction that cosmologists made about the cosmic web that I find fascinating. It's about something called the warm-hot intergalactic medium, or WIM. The idea is this. Most of the normal matter in the universe isn't in stars or galaxies. It's in the intergalactic medium. But when astronomers added up all the matter they could see, stars, gas clouds, the hot gas in galaxy clusters, they found they could only account for about half of the normal matter that should exist based on observations of the early universe. The rest was missing. Astronomers called it the missing baryon problem. Where was all the normal matter? The answer, they think, is the WIM. It's gas that's been heated to temperatures of 100,000 to 10 million degrees by the gravitational collapse of structure in the cosmic web. It's too hot to emit much visible light, and too diffuse to be easily detected. But it's there, filling the filaments, contributing to the structure. And slowly, over the past couple of decades, astronomers have started detecting it. Using X-ray telescopes, looking for the faint signature of hot gas along the filaments. Using techniques like measuring the absorption of light from distant quasars, looking for the imprint of the WIM in the spectrum. They're finding it. The WIM is real. The filaments aren't empty. They're filled with this hot, diffuse gas, the ordinary matter that traces the dark matter skeleton of the cosmic web. It's not much. The density is incredibly low, but it's there, and it accounts for the missing baryons. I want to talk about scale again, because I think it's easy to lose sight of just how large these structures are. A filament might be 500 million light-years long. Let's try to put that in perspective. Light from one end of the filament, traveling at the speed of light, the fastest anything can go, would take 500 million years to reach the other end. That's longer than complex life has existed on Earth, longer than the dinosaurs lived and died, longer than the continents have been in their current configuration. If you started at one end of the filament and traveled toward the other at a significant fraction of the speed of light, say 10%, which would be an astonishing speed for any spacecraft we can imagine, it would take 5 billion years to get there, longer than the Sun has existed. These are not distances we can travel, not with any technology we have or are likely to have. They're not even distances we can think about in any intuitive way. Our brains didn't evolve to comprehend scales like this, and yet the universe is full of them. The cosmic web operates on these scales. Galaxies flow along these distances. Structure forms and evolves over these timescales. We're embedded in something vastly larger than ourselves, larger than our planet, our solar system, our galaxy. We're part of a structure that spans a significant fraction of the observable universe. Here's something interesting. The cosmic web isn't uniform. Some regions are more densely connected than others. There are areas where multiple filaments converge, creating what's called a supernode. These are the locations of the largest galaxy clusters and superclusters. They're the most connected places in the universe, gravitationally speaking. Matter flows toward them from all directions. And then there are regions where the web is sparser, where filaments are thinner, more spread out, where the voids are larger. Our location in the cosmic web, embedded in a filament that's part of the Virgo supercluster, is fairly typical. We're not in a supernode, but we're not in the middle of nowhere either. We're in a reasonably well-connected region. That's probably good for us. If we were in a void, isolated from other galaxies, we might not exist. The processes that led to the formation of the Milky Way, the Sun, the Earth, might not have happened the same way without the environment provided by the filament. So, in a sense, the cosmic web isn't just where we are, it's part of the reason we are. Let's talk about observations for a moment. How do we actually see the cosmic web? As I mentioned before, we map it by measuring the positions and distances of millions of galaxies. But that's not the only way. There's a technique called the Lyman alpha forest that lets us probe the intergalactic medium directly. Here's how it works. Light from distant quasars, incredibly bright, active galactic nuclei, travels through space for billions of years before reaching us. Along the way, it passes through clouds of hydrogen gas in the intergalactic medium. Each cloud absorbs a little bit of the light at a specific wavelength, corresponding to the energy needed to excite hydrogen atoms. When we look at the spectrum of a quasar, the breakdown of its light into different wavelengths, we see a series of dark lines. Each line represents a cloud of hydrogen somewhere between us and the quasar. The more lines, the more clouds. And by measuring the wavelength of each line, we can determine how far away the cloud is. This gives us a one-dimensional map of the intergalactic medium along the line of sight to the quasar. And if we observe many quasars in different directions, we can start to build up a three-dimensional picture. What we see matches the cosmic web. The hydrogen is concentrated in the filaments, tracing the distribution of dark matter. The voids show up as regions with very few absorption lines, not much hydrogen there. It's a beautiful confirmation of the theory. The cosmic web isn't just a pattern in the distribution of galaxies. It's a real, physical structure that affects the distribution of gas, the bending of light, the motion of matter. Here's a detail I find compelling. The cosmic web is, in a very real sense, the result of quantum fluctuations in the early universe. In the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion called inflation. During inflation, quantum fluctuations, tiny random variations in the energy field driving inflation, were stretched to cosmic scales. When inflation ended, those quantum fluctuations became density fluctuations, regions that were slightly denser or slightly less dense than average. And those tiny differences, 1 part in 100,000, were the seeds of all the structure we see today. So the cosmic web, the filaments, the clusters, the voids, all of it traces back to quantum randomness in the first moments of the universe. The universe rolled the dice, in a sense, and the cosmic web is the outcome. It's almost philosophical. The largest structures in the universe have their origin in the smallest possible fluctuations. The cosmic and the quantum are connected. Let's slow down even more. Let's think about what it means to be in a void. There's a concept in physics called homogeneity. It means that something looks the same everywhere. The universe, on the largest scales, is homogeneous. If you zoom out far enough, one region looks like any other. The same average density, the same cosmic web pattern, the same ratio of filaments to voids. But locally, the universe isn't homogeneous at all. There are stars and empty space, galaxies and intergalactic medium, filaments and voids. A void is, in a way, the closest the universe gets to homogeneity on a local scale. In a void, matter is spread out almost evenly. There's very little structure. It's the universe in its simplest state. And there's something peaceful about that. Not peaceful in the sense that you'd want to be there. It would be profoundly lonely, as I said before, but peaceful in the sense of simplicity, lack of complication. In a filament or a cluster, there's constant activity, galaxies interacting, stars forming, supernovae exploding. Even if it's all happening on timescales of millions of years, it's still dynamic, still changing. In a void, things are quieter. The few galaxies that exist evolve slowly. Space expands. Dark energy does its work. But there's no drama, no cosmic violence, just stillness. I want to return to dark energy for a moment, because it's central to the future of the cosmic web. Dark energy is a form of energy that permeates all of space. It doesn't clump or concentrate. It's the same everywhere. and it has a strange property. It exerts negative pressure. It pushes space apart. We don't know what dark energy is. It might be the energy of empty space itself, the so-called cosmological constant that Einstein introduced into his equations and later called his greatest blunder. Or it might be something more dynamic, a field that changes over time. But whatever it is, it's causing the expansion of the universe to accelerate. In the distant future, dark energy will dominate the dynamics of the universe. Gravity will still hold together structures that are already bound, galaxy clusters, for instance, but everything else will drift apart. The filaments will thin, the voids will grow. Eventually, each galaxy cluster will be isolated, surrounded by an expanding void that grows larger and larger, until no light from any other structure can reach it. The observable universe, from the perspective of that cluster, will shrink to just the cluster itself. And billions of years after that, dark energy might even start to pull apart structures that are currently bound. This is called the Big Rip. It's a speculative scenario, dependent on the properties of dark energy, but it's possible. In the Big Rip, galaxy clusters would eventually be torn apart, then galaxies, then stars, then planets, then atoms. But that's so far in the future, if it happens at all, that it's almost abstract. For now, the cosmic web is stable. Still evolving, yes, but stable. Let's think about what the cosmic web tells us about the universe as a whole. It tells us that the universe is old. It takes billions of years for structures like filaments and clusters to form. The fact that we see such well-developed structure is evidence that the universe has had time to evolve. It tells us that the universe started in a very smooth, uniform state. If the early universe had been clumpy, with large density variations, we wouldn't see the kind of structure we do. The cosmic web is the result of tiny initial fluctuations amplified by gravity over time. It tells us that dark matter and dark energy are real. Without dark matter, structure would be much weaker. Without dark energy, the expansion of the universe would be decelerating, not accelerating, and it tells us that we're not special. The cosmic web looks the same everywhere. Our place in the universe is typical. We're part of the structure, but we're not at the center of it. There is no center. This last point is important. It's easy to look at images of the cosmic web and think of ourselves as outside it, looking down on it. But we're not. We're inside. We're one thread in the tapestry. Here's something that I think about sometimes. Every photon of light that reaches us from a distant galaxy has traveled through the cosmic web. It's passed through filaments, skirted voids, maybe been bent by the gravity of a cluster or two. The light carries information, not just about the galaxy it came from, but about everything it passed through on the way. It's a message that's been shaped by the structure of the universe. When we look at distant galaxies, not just seeing those galaxies, we're seeing the cosmic web itself imprinted on the light. That's what gravitational lensing reveals. That's what the Lyman alpha forest measures. That's what redshift surveys map. We're using light as a probe, tracing the invisible architecture of the universe. Let's talk about one more void before we move to part 3. There's a region of space called the local void. It's not as large as some of the other voids we've discussed, only about 150 million light-years across. But it's close to us. We're on the edge of it. The Milky Way sits in a filament, as I've mentioned, and that filament borders the local void. If we look in the direction of the void, we see very few galaxies. It's one of the emptiest regions of the nearby universe. And here's the interesting part. We're being pushed by the local void. Voids, despite being underdense, still have a gravitational effect. They don't pull things toward them, obviously. There's not enough mass for that. But they do push things away. Or more accurately, the filaments and clusters surrounding the void pull matter toward themselves, and that creates a net effect that looks like the void is pushing. The Milky Way and the whole local group is moving away from the local void at about 200 kilometers per second. It's a small component of our overall motion through space, but it's measurable. We're being influenced by the emptiness nearby. Even voids leave their mark on the motion of galaxies. All right, we've spent a lot of time in the quiet places. The voids, the empty spaces, the dark matter scaffolding that holds everything together. In part 3, we'll step back and think about what all of this means. Not in a scientific sense, we've covered the science, but in a more reflective sense. What does it mean to be part of the cosmic web? To be embedded in this vast structure? To know that we're connected to everything, even across distances we can barely comprehend? We'll slow down even further. We'll let the ideas breathe. And we'll find a place to rest at the end. We've come a long way together, through the filaments, the clusters, the voids. We've thought about dark matter, dark energy, the scaffolding of the universe. We've tried to comprehend distances and timescales that don't fit comfortably in a human mind. In this final part, I want to take a step back. I want to talk less about the science, though there'll still be some, and more about what it all means. Or maybe what it doesn't mean. How we fit into this picture, and why, in the end, I think there's something quietly comforting about the cosmic web. Let's take our time. It's a strange feeling, isn't it? To realize you're part of something you can never fully perceive. You can see the stars. On a clear night, away from city lights, you can see the Milky Way stretching across the sky, our galaxy, seen from within. You can even see Andromeda if you know where to look. A faint smudge of light that's actually an entire galaxy, 2.5 million light-years away. But you can't see the filament we're in. You can't see the Virgo supercluster. You can't see the cosmic web. These things are too large, too diffuse, too dependent on perspectives we don't have. To see the cosmic web, you'd need to be outside the universe, looking down on it. And that's not possible. So we infer, we map, we measure, we build models and simulations. And slowly, over decades of work by thousands of astronomers, we piece together a picture of the structure we're embedded in. It's an astonishing achievement when you think about it. We're one species, on one planet, in one galaxy, in one tiny corner of the universe. And yet we've managed to map the largest structures that exist. We've figured out the architecture of the cosmos. That says something about the power of science. About what's possible when you combine curiosity, patience, and the willingness to follow evidence wherever it leads. But it also says something about us, I think. About our need to understand, to find patterns, to make sense of things. Humans have always looked up at the sky and wondered. We've told stories about the stars. We've used them to navigate. We've tracked their motions and tried to find meaning in them. The cosmic web is the latest chapter in that story. It's the pattern we found when we zoomed out to the largest possible scale. It's not a story we invented. It's real. It's physical. It's out there whether we observe it or not. But it's a story we've uncovered. And I think there's something deeply human about that. We're meaning-making creatures. We look at chaos and we find order. We look at randomness and we find patterns. The cosmic web is a pattern. But it's also, in a sense, a reflection of us. Our desire to understand. Our refusal to accept "I don't know" as a final answer. Let's talk about isolation and connection for a moment. On the one hand, the cosmic web tells us we're connected. The Milky Way is part of a filament. That filament connects us to other galaxies, other clusters, all the way out to the edges of the observable universe. There's a path. Purely gravitational, purely structural, but still a path, from here to anywhere. We're not alone. Not in the universe. We're part of a network. But on the other hand, the cosmic web also highlights how isolated we are. The distances are too large to cross. The timescales are too long. We're connected in structure, but separated in every practical sense. The light from a galaxy in a distant filament takes billions of years to reach us. By the time we see it, the galaxy has changed, evolved, maybe merged with others. We're not seeing it as it is now. We're seeing it as it was. And it's seeing us, if anyone there is looking, as we were billions of years ago, in the past. A past so distant that the Earth might not even have existed yet. So we're connected and isolated at the same time. Part of the web, but unable to interact with most of it. That's a strange duality. There's a thought that comes up sometimes when people learn about the scale of the universe. It's something like, we're so small, so insignificant. What does any of this matter? And I understand that feeling. The universe is vast. We're tiny. Our whole planet is a speck of dust in a galaxy that's itself just one among hundreds of billions. But I don't think that makes us insignificant. Significance isn't about size. It's not about duration. It's not about how much space you take up or how long you last. Significance is about complexity, about awareness, about the ability to understand. And in that sense, we're not insignificant at all. We're the universe understanding itself. We're matter that has arranged itself in such a way that it can look back at the larger structure and comprehend it. That's rare. As far as we know, it might be vanishingly rare. There might be billions of planets out there, and billions of opportunities for life to arise. But we don't know how often life becomes conscious, becomes curious, becomes capable of science. Maybe often, maybe rarely. We don't know yet. But we do know that it happened here, on Earth, in this particular corner of this particular filament. And that's extraordinary. Let me tell you about a simulation. Cosmologists build computer simulations of the universe. They start with the initial conditions, the tiny density fluctuations in the early universe, and then they let the simulation evolve. They apply the laws of gravity and fluid dynamics and watch what happens. And what happens is, the cosmic web emerges. Filaments form, clusters grow, voids expand. The simulated universe looks like the real universe. This is powerful confirmation that we understand the basic physics, that our theories of gravity, dark matter, and dark energy are on the right track. But here's what I find compelling about these simulations. They're deterministic. If you run the simulation twice with the same initial conditions, you get the same outcome. The filaments form in the same places, the clusters grow to the same sizes. But if you change the initial conditions even slightly, if you adjust the tiny quantum fluctuations by a small amount, you get a completely different cosmic web. The filaments form in different places. The clusters have different masses. The overall pattern is similar, but the details are unique. This means that the specific structure of our cosmic web, the exact positions and shapes of the filaments, the precise locations of the voids, all of that is contingent. It depends on the specific quantum fluctuations that happened in our universe in the first moments after the Big Bang. If the universe had started with slightly different initial conditions, the cosmic web would be different. The Milky Way might not exist. Or it might exist, but in a different location, a different filament. We're the product of a specific history, a specific roll of the quantum dice. That's humbling in a different way. Not because we're small, but because we're contingent. We exist because of a particular sequence of events, stretching back to the beginning of time. Change any one of those events, and we might not be here. Let's think about the future again. Not the far future, the trillions of years from now, when dark energy has torn everything apart. But the nearer future, the next billion years or so. The Milky Way and Andromeda are going to collide. This has been known for a while. Andromeda is moving toward us at about 110 kilometers per second. In about 4 or 5 billion years, the two galaxies will pass through each other. Stars won't collide. The distances between stars are too large for that. But the gravitational interactions will be intense. Both galaxies will be disrupted, stretched, pulled apart, and then pulled back together. Eventually, they'll merge. They'll become a single larger galaxy, probably elliptical in shape, having lost the spiral structure both galaxies currently have. And the local group, our small collection of galaxies, will effectively cease to exist as a separate entity. It'll become part of a larger structure, a merged galaxy that some astronomers have already nicknamed Milkomeda. This is the future of our corner of the cosmic web. Not destruction, exactly, more like reorganization. The matter that makes up the Milky Way and Andromeda won't go anywhere. It'll just be rearranged. New stars will form from the gas that's stirred up by the merger. Old stars will find themselves in new orbits. The Sun will probably survive the merger. It'll be thrown into a new orbit around the center of Milkomeda, but the chances of it directly interacting with another star are incredibly small. And if there are any descendants of humanity around to witness this, biological or otherwise, they'll see a very different night sky. No more Milky Way arcing overhead. Instead, they'll be inside a giant elliptical galaxy, with old stars scattered in all directions and relatively little gas and dust. It'll be a quieter galaxy, in a sense, less star formation, more evolution toward a stable, settled state. But it'll still be part of the cosmic web, still embedded in a filament, still connected to the larger structure. The cosmic web operates on timescales longer than the life of individual galaxies. It's patient. It changes slowly, but it does change. Here's something that doesn't change, though: the fundamental nature of gravity. Everything we've talked about, the formation of structure, the filaments, the clusters, the voids, all of it is driven by gravity. Gravity pulling matter together. Gravity amplifying the initial density fluctuations. Gravity carving the universe into the patterns we see. Gravity is the architect of the cosmic web. And gravity is strange. It's the weakest of the 4 fundamental forces, by far. Electromagnetism is vastly stronger. The strong nuclear force is vastly stronger. But gravity has 2 properties that make it dominant on large scales. First, it's always attractive. It never repels. Unlike electromagnetism, where positive and negative charges can cancel out, gravity just adds up. More mass means more gravity. And second, it has infinite range. It falls off with distance, following the inverse square law, but it never goes to zero. Every particle in the universe is gravitationally attracted to every other particle, no matter how far apart they are. So, on cosmological scales, gravity wins. It's the force that shapes the universe. Dark energy might be pushing space apart, but gravity is what creates structure within that expanding space. It's the reason we have galaxies, stars, planets. It's the reason we exist. We are, in a very direct sense, products of gravity. Let me bring this back to something more personal for a moment. You, right now, are made of atoms. Hydrogen, carbon, oxygen, nitrogen, and trace amounts of dozens of other elements. Those atoms were forged in stars. Most of them came from stars that exploded as supernovae, scattering their contents into space. Some came from the Big Bang itself. The hydrogen in your body is primordial, almost as old as the universe. Those atoms drifted through space. They became part of the interstellar medium. They were pulled by gravity into the filament that would become our home. They condensed into a cloud of gas that collapsed under its own gravity to form the sun and the planets. They became part of the Earth. They cycled through geological processes. They became part of living organisms. And eventually, through an unbroken chain of events stretching back 4.5 billion years, they became part of you. You are a piece of the cosmic web. Literally. You're not separate from it. You're not an observer looking at it from the outside. You're made of it. The calcium in your bones was created in a star that lived and died in our filament. The iron in your blood was forged in a supernova that helped shape the structure of the Milky Way. The oxygen you're breathing right now has cycled through countless stars and countless planets. You're recycled stardust. That's not a metaphor, it's just true. And here's the thing. That stardust is aware. It's thinking. It's wondering about its origins. That's what you are. Matter that has arranged itself in such a way that it can contemplate the universe it came from. I know I've said this before, but it bears repeating, because it's genuinely astonishing. The universe spent billions of years creating the conditions for complexity. Stars had to form and die, scattering heavy elements. Planets had to form and cool. Oceans had to develop. Chemistry had to become biochemistry. Single cells had to become multicellular organisms. Nervous systems had to develop. Brains had to evolve. And all of this happened because of the cosmic web. Because the structure of the universe created the pockets of high density, galaxies, solar systems, planets, where complexity could arise. In the voids, none of this happens. In the voids, matter stays simple, spread out, undisturbed. But in the filaments, in the clusters, in the dense regions where matter has congregated, you get stars, planets, life, thought. We exist because the universe is structured, because it's not uniform, because gravity has carved it into patterns. The cosmic web isn't just where we are, it's why we are. Let's talk about time one more time. Not cosmic time, but human time. A human life is about 80 years, if you're lucky. That's nothing on the timescale of the universe. The cosmic web evolves over billions of years. Galaxies take hundreds of millions of years to traverse filaments. Stars live for millions or billions of years. From the perspective of the cosmic web, human history is instantaneous. The entire span from the first cities to the present day is a fraction of a second in cosmic terms. And yet, in that tiny sliver of time, we've figured out the structure. We've mapped the filaments. We've inferred the existence of dark matter. We've measured the acceleration of the universe. We've done all of this in the blink of an eye, cosmically speaking. That's remarkable. We're ephemeral, yes. Our individual lives are brief, but collectively, we've achieved something that transcends our individual lifespans. We've built knowledge that will outlast us. That's already outlasting the people who first contributed to it. Science is a transgenerational project. It's humanity's way of cheating time. We live for decades, but our understanding can accumulate over centuries, millennia even. And that understanding connects us, not just to each other, but to the universe. We're part of the cosmic web physically, yes, but we're also part of it intellectually. We understand it, we can describe it, we can explain how it came to be. That's a kind of connection that transcends distance and time. I want to talk about the limits of our knowledge, because as much as we've learned, there's still so much we don't know. We don't know what dark matter is made of. We've narrowed down the possibilities, but we haven't detected it directly. It remains one of the biggest mysteries in physics. We don't know what dark energy is. We can measure its effects, but we don't understand its nature. Is it the cosmological constant? Is it a field that changes over time? We don't know. We don't know how common life is in the universe. We know it arose at least once, here on Earth. But we don't know if it's common or rare. We don't know if intelligence is an inevitable outcome of evolution or a fluke. We don't know what happened before the Big Bang. We don't even know if that question makes sense. Time itself might have begun with the Big Bang, in which case there is no before. We don't know if our universe is the only one. There are theories, speculative but mathematically sound, that suggest there might be a multiverse. Other universes with different physical constants, different structures, different histories. We don't know if that's true. These are big questions, fundamental questions, and we don't have answers yet. But that's okay. That's the nature of science. You answer one question, and it opens up 10 more. Understanding is a process, not a destination. And the cosmic web is part of that process. It's a piece of the puzzle. A big piece, but still just a piece. Let me share a moment of silence with you. Just a moment. Sometimes, when I think about the cosmic web, I don't think in words. I just try to hold the image in my mind. Filaments stretching across the darkness, clusters glowing at the intersections, voids, vast and empty, all of it held together by invisible gravity, by dark matter, by forces we can barely comprehend. And I let that image sit. I don't analyze it. I don't try to explain it. I just experience it. There's something meditative about that, something that quiets the mind. The cosmic web is too large to grasp intellectually, really. You can understand the physics, you can work through the equations, but to really feel the scale, the vastness, the interconnectedness, that requires something different, something more intuitive. So sometimes I just sit with it and let it be what it is. Maybe you can do that now too, just for a moment. Let the ideas we've talked about settle. Don't try to remember them all. Don't try to analyze them. Just let them be part of your awareness for a moment. All right, let's come back. I want to end by thinking about perspective, about where we stand, not physically, but conceptually, in relation to the cosmic web. For most of human history, we thought we were at the center of everything. The Earth was the center of the cosmos. The sun and the planets and the stars all revolved around us. Then we learned that wasn't true. The Earth orbits the sun orbits the center of the Milky Way, The Milky Way is just one galaxy among billions. Each discovery pushed us further from the center, made our position less special. And the cosmic web is the culmination of that process. It tells us there is no center. The universe is roughly the same everywhere. Our filament is like any other filament. Our cluster is like any other cluster. There's nothing special about our location in the cosmic web. That could be depressing. It could make us feel insignificant, unimportant. But I don't think it does, or at least it doesn't have to. Because here's the thing. We're not special because of where we are. We're special because of what we are. We're the part of the universe that knows it's part of the universe. We're the part that can look back and understand. And that doesn't require being at the center. It doesn't require being in a special place. It just requires being complex enough and curious enough to ask the questions. There's a photo that some people know about. It's called the Hubble Ultra Deep Field. It's an image taken by the Hubble Space Telescope showing a tiny patch of sky about the size of a pinhead held at arm's length. In that tiny patch, there are about 10,000 galaxies. 10,000. Each one containing billions or hundreds of billions of stars. Each one sitting somewhere in the cosmic web, part of a filament or a cluster or maybe a void. And that's just one tiny patch. The entire sky contains billions of similar patches, billions of similar collections of galaxies. The universe is full of structure, full of complexity, full of matter arranged in intricate patterns. And somewhere in one of those galaxies, in one of those patches, there's us, thinking about all of it. That photo always makes me feel two things at once. Small, yes, but also connected, because all of those galaxies are part of the same web, the same structure, the same universe. We're not alone in it. We're embedded in it, part of it. I think a lot about the word cosmos. It comes from a Greek word meaning order or arrangement, the opposite of chaos. The ancient Greeks used it to describe the universe because they saw it as ordered, structured, governed by laws that could be understood. And they were right. The universe is ordered, it's structured. The cosmic web is the clearest expression of that structure on the largest scales. But it's not a rigid order. It's not static. It's dynamic, evolving, changing over time. The filaments shift, galaxies flow, voids expand. The whole thing is in motion, even if it's motion we can't directly perceive. And that's beautiful, I think. The universe is ordered enough that we can understand it, but dynamic enough that it's always changing, always offering new things to discover. The cosmic web is a snapshot. It's the structure as it exists now, in this particular epoch of cosmic history. It was different in the past. It'll be different in the future. But right now, in this moment, it's this. Filaments and clusters and voids. Galaxies flowing along invisible highways of gravity. Dark matter holding it all together. Dark energy pulling it all apart. It's the cosmos, the ordered universe, and we're part of it. I want to end with something simple. Tonight, if you can, look up at the sky. Find a dark place if you're able. Let your eyes adjust to the darkness. You won't see the cosmic web. You won't see the filaments or the clusters or the voids. But you'll see stars. And those stars are part of the Milky Way. And the Milky Way is part of a filament. And that filament is part of the cosmic web. Everything is connected. You're not separate from what you're looking at. You're made of the same stuff. You're part of the same structure. You're embedded in the same web. And maybe there's something comforting in that, something grounding. You're not alone. You're not isolated. You're part of something vastly larger than yourself. The cosmic web doesn't care about you, in the sense of having thoughts or intentions, but it's your home, the structure you're part of, the context in which you exist. And now you know about it. You understand it, at least a little. You've traced the filaments in your mind. You've drifted through the voids. You've thought about the dark matter and the dark energy and the scales of time and distance that define the universe. That's not nothing. That's knowledge. That's understanding. That's connection. So, wherever you are tonight, I hope you feel a little bit more connected, a little bit more embedded, a little bit more at home in the universe. Because you are home. You've always been home. You're part of the cosmic web. And that's a beautiful thing to be. Thank you for listening. Thank you for taking this journey through the hidden structures of the universe. I hope it's given you something to think about, something to wonder about, maybe something to dream about. From all of us here at ZzScience, good night, sleep well, and keep looking up.